Okay, so here we go. Yes, caffeine bioavailability through the roof is correct statement, and that's a good way to start the lecture. So today we're going to talk about static equilibrium. And let me just hit pause over here. Let me start just by giving you some examples and some basics here before we get to the book. And I think if you wanted to have your book open, just so you know, so you're approximately right, we're starting chapter 12 on page 99. Page 99, if you want it. It's that big list. Okay. Page 99. Now, I'm going to run through this. I'm going to cover chapter 12, at least the parts that you need to know. All right. Okay, we're done lecturing on chapter 12. Believe it or not, it's that simple. Sum of torques equals 0, and sum of forces equals 0. Now, there's a couple of weird questions later on at the end. Maybe they're a little different. We'll talk more. But effectively, this is and you may be saying, well, don't we already know that from chapter 10 and from chapter 5 and 6? Yes. However, in practice, there are a number of geometry tricks. So what you're really going to be learning in this chapter is a bunch of geometry. And so this is important for anybody that wants to take any other physics classes. You have to be good with geometry. And it tied into that geometry, and maybe there's some trig. And then there's also a bunch of tricks associated with doing the right-hand rules and coordinate systems. So to be honest, this is really stuff you should be able to do without any lecture. But in practice, there's so many subtle tricks. It's like, yeah, it's like doing chapter 10 or a subset of chapter 10, the torque portion, and learning to really be a master of it. Okay, so let me start with why you might care about this. Give me a sec. Excuse me. Okay, this thing's heavy. Okay, so imagine you have this thing here, and maybe I'll actually flip this. Let me just erase this board. Oh my gosh, come on now. This is getting to be a circus. Just so you don't have so much distraction in the background. Okay, here's the idea. I got a plank, got a 2x4, and just some rod here, some 1x. There's a pivot point right here. I don't know if you can see that. Right near my fingers, there's a pivot point, little hinge there. Up here, there's a scale. And then I could put a mass on here at different spots. And I could also move this to different spots. So let's start with the easy one here, like that. So now there's a string. You might not be able to see it, but there's a string right there. And I could put this mass on here like this. Now, the whole point of this chapter is thinking about what happens to the tension in the string and the forces at the pivot if the mass is in different places. And for example, or what if you use a different size mass? And what is the use of this? Well, you could figure out how big the string needs to be so it doesn't break. And you could figure out how big the bolts need to be so that they don't fall out of the wall or get pulled out. And if you're a mechanical or civil engineers, you could even get as intricate as saying, what about the thread size and the pitch? What threads do I need to use on the screw so that it doesn't pull out of the wall? And then I get a bunch of complaints, and then I have to issue a bunch of refunds and safety recalls and blah, 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 blah. So this is really basic stuff, but it's extremely useful. What if you're a civil engineer? I think you could see immediately the practicalities of a civil engineer, making sure your bridges don't fall down, right? And you might be saying, what about biology? Again, most of it is really the geometry and such. And same for chemists, learning a bunch of geometry will not hurt you in your other physics classes and your others. But I do like to think about one practical biological application. You can think about levers in the human body, right? And what about putting a human being in traction? And by that, to adjust the healing process. What tension do you need to put on their leg so that they're going to heal in the most rapid way? And then if you need such and such a mass, or if you need such and such a tension, what should you put for the hanging mass, etc. And so there are applications all over in kinesiology and other types of things. But this is kind of the main thing, is what we're trying to figure out. What strings do we need to use? What pivots do we need to use? What bolts do I need to use? What threads, etc. That kind of stuff. Now, we are going to focus on the big picture above that. We're just going to focus on getting forces rather than the nitty-gritty details of thread counts and stuff. So we're going to just focus on torques and forces. And depending on what your major is, you could use that in detail for some calculation in some other course. All right. Questions before we get into it? All right, let's go with the screen share. We'll come back to that and do the math on that problem later. I'm going to start with some easier ones. Whoops. What page did I say it was? 99, I think. There we go. All right. Oops, let me get this here and move this around. All right. So the key to doing this, you're going to hear me babble over and over and over about this. Draw. Sketch. Draw a separate sketch. Draw. Okay. That's the key. And if you're drawing pictures, let me give you a figure, a scale here. So like, let's say this is your piece of paper, right? Or whatever. You don't want to be drawing pictures this big. You want to be drawing pictures this big. So, a quarter of a page. And what you might do is you might draw one figure here that is showing you all the lengths and angles, but no forces. And then over here, you might show a different picture that has only the forces. Oh, that's called an FBD. So we're basically needing to do separate pictures to get all the angles and distances, and then a separate FBD. And so this is the first chapter where an FBD is actually really useful to draw it separate. Up till now, we could kind of get away with just drawing just one object all by itself with a bunch of arrows shoved in there. All right. And what I mean by this, let me just walk you through a nasty looking one, and then we'll come back to this. So I'm going to try and explain this checklist, but first let me just show you a nasty solution here. Look at this one right here. It's actually similar to what we were just looking at. I draw one picture just with the lengths and the angles. I draw a separate FBD. I write down force equations and torque equations. I solve for something. That's the main thing that we are trying to do. Now, in practice, sometimes this gets really nasty. Look, there's two different objects. We see it's critical to draw the forces where they apply. All right, let me see. Here's another one. Ooh, look at this one. Look at the different, look at how many different pictures I'm drawing for these simple sounding problems. And look at all this trig and geometry, basically. So let me show you another one in here. Here's one way to do this problem. And I drew, look at how many pictures I'm drawing, right? And then I even said, you know what, let's try this problem another way. And I drew two more pictures to do it the other way. And one of the things you will see here is different problems have different strong methods of solution. Like this one, the clever way to do it is to use lever arms. But if you didn't see that, you could still do it these other ways. Sometimes it's nice to draw pictures with the forces as their full vectors. And other times it's nice to draw pictures with just the components, like this lower one. And so there's no way to see all this stuff unless you practice and draw it yourself. So I drew tons of pictures for you. And yeah, look at this one picture, this one problem. I did it 1, 2, 3, 4, 5 different uh 5 different ways. So or a couple 5 different diagrams to show you 3 different methods of solution. So drawing lots of pictures, being neat and large size pictures so you could waste less time. Yes, you're wasting a little more paper. I'm not going to lie to you, right? When you draw those big pictures, you use up more paper. But if it means understanding the problems more rapidly, it's not waste. It's useful. And then you actually waste less paper because you don't have to retake this course when these questions show up on your final and kick your ass because you'll know how to do them. So that's being environmentally conscious, is solving this class on the first time through if you can. All right, that's today's weird eco whatever. All right. Let's go now check out this checklist. So if you're wondering, whoops, that's not what I want to talk about. Come on, computer. There we go. Let's go through this. This is a strategy for success for these types of problems, even though they sound easy. It will not always be the smartest way to do these problems, and I'll explain why in just a minute. It is usually the smartest way to do the problems. Most particularly is bullet 2. Well, I'll explain. First, draw these pictures and do a separate sketch showing lengths and angles without any forces so you don't get lost. Don't forget the reaction forces at the pivot. Don't forget those. Now, usually, but not always, we do sum of torques first. Every once in a while, you might do forces first. Okay, that's the only thing that's kind of weird here. Sometimes you do torques and you never bother to do forces. So in a lot of problems, doing sum of torques will solve the problem for you. Some problems it won't work that way. That's why I suggest doing torques. To be clear, I don't know if you saw what I was doing is sometimes I draw a separate sketch. Okay, so sketch the problem, basically do an FBD, clearly showing the pivot point. And don't forget to specify what's positive, clockwise or counterclockwise, because you could choose whichever way you want. Okay. Remember, you got to figure out this stuff here, these 4 different methods. Obviously, there's some vectors in here that we should be discussing, but I don't want to go into that. Obviously, these last 3 are magnitudes, but you can get the direction with the right-hand rule. So maybe I'll just mention that for posterity's sake. If you need the direction, you use the right-hand rule. All right. So draw a big picture for angles, do a free body diagram, do torques. Then I usually do sum of forces. Only in rare cases do I switch up steps 2 and 3, but you still have to do both of them. Watch out, world. Sometimes sometimes I will redraw the FBD. I know it sounds crazy, even though you're like, well, dude, I just did an FBD for torques. Sometimes it helps to draw a separate FBD. In particular, let me show you one. Well, there was one that works, but I want to show you that drawbridge one. This drawbridge one is a great example. The issue here is if you use this one FBD, this is sum of forces in the X. This here is sum of forces in the Y. And this last one is sum of torques. Now, I want to point out one thing here, just to show you why you might do this. Look at the angle that appears on the tension. Alpha appears in the force equations, but beta appears in the torque equation. What we see here is it can get tricky. The angles that show up in one equation might not show up in another equation at all. Notice there's no alphas in here. And this one, you could write it with beta plus 5 or with alpha, depending on how you do that. Oh my goodness. That is why I am saying sometimes, rather than just having one FBD, you could do one FBD for the torque and clearly show the angle you need, and do a separate FBD for the forces, if that helps. All I want is people to pass and actually know their material. So just be aware of that. And this is why I'm saying, do not assume the forces are going to split up the same way they would in your torque diagram. Let me show you that again. If you were doing this problem as a torque, there would be a torque parallel or a tension parallel, and then there's a tension perpendicular to the rod. But that's not the same as tension in the Y and tension in the X, right? That's what I'm saying here. The forces perpendicular to the rod may not line up with the standard XY axis. And whether you like it or not, you are going to discover almost everybody, including yourself, will do a standard XY for the forces. You could say, why don't I rotate it? No, don't do it. It's a bad idea. You'll screw up the gravity terms, period. All right. Now, you got 3 equations, you got 3 unknowns, solve for something, do some work. All right. One thing I should mention here, let me be clear. Point 2a. I'll just show you what I mean by this. In this problem, right now, if I could hold it still, I hope you agree this rod is not rotating. Well, if I could not bump it. It's not rotating about this pivot point, but it's also not rotating about its center. It's also not rotating about the end. And this is a really cool thing about chapter 12. You could do sum of torques about this point, that point, about Compton, about Inglewood. You could go any way you like it, right? So you could even use Lompoc. We could go sum of torques about now, there's 3 obvious spots here, maybe 4, right? What if this is located right here? There's 3 obvious spots here. You could do sum of torques about the obvious pivot, sum of torques about this mass, sum of torques about the center mass of the rod, or sum of torques about the end. The advantage of choosing different points is what? What happens if I choose this point to do sum of torques? Does anybody see where I'm going with this? When you do sum of torques about this point, which forces drop out? What do you think? If we do sum of torques about this point.
Gravity?
No. I see. This is payback for all. You guys are making me hold this extremely heavy demo. I'm going to be sweating here. Make me work for it, will you? What forces act at the pivot? What do we call those all the time?
Reaction force?
Yeah, those don't show up in the torque equations. If I choose this point, this force drops out. If I choose this point, center of mass drops out. If I choose that point, what force drops out? Tension. The idea is you could choose different points depending on which thing in the problem is unknown. If I give you something and say, you don't know the tension, maybe you want to eliminate it by choosing that point to write your force equations or torque equation, excuse me. So the advantage of choosing different points is you can eliminate forces you don't know about. Usually, though, we don't know shit about the pivot. So, right? And so what you typically do is you do sum of torques about the obvious pivot, crank everything out and figure out the tension in the cable or the weight or whatever. Then you could go back and use your force equations to then figure out the reaction force at the pivot. That's a very typical procedure. All right, let's do some work. Right. Go ahead.
So if I'm understanding correctly, we want to choose different pivots because depending on the angle, like certain force vectors are not going to affect the overall force equations.
Let me show you in this first one. I literally do it in the first one. Is that okay, Gonzalo?
Yeah.
All right. So I'm going to start with the really simple one. I'm going to start with 12.1. Let's take out all the angles for now just to keep it easy. Okay. So you get this set up. I'm going to draw it on my whiteboard. Okay. And I promise to get to that, Gonzalo. And if I forget, remind me as I try to move on. Okay. So 12.1. Normally, this is a classroom demo, but we're not in a classroom. So I'm going to walk you through it as if we're in a classroom. Give me a second to draw it up. NA, NBX. Okay. Okay. So this is the problem. Normally, I actually built this and we could lay down on it and measure people's center of mass. But let's say we know that this distance here is some length L. All right. Now, the person's center of mass is probably right about here in their belly button, approximately. Now, this scale on this end is pushing upwards with NA, meaning some normal force. The other scale is pushing up with some size NB. Maybe they're the same, maybe they're different, who knows? And now, technically, what kind of force does the person exert on the board? What type of force? Is it frictional? What type of force does the person exert on the board? If it helps, think of the person as a block.
What do you say, normal?
Normal force. So technically, there's a normal force from the person on the board. However, in this case, what's the acceleration of this entire thing right now, if you had to guess? Zero. So what should be true about this normal force and the person's weight?
Equal.
They should be equal. Now, there's actually a chain of reasoning here. Think about it. The normal force that the board exerts on the person has to equal the person's weight. By Newton's third law, the normal force that the person exerts on the board is equal to the normal force that the board exerts on the person. Therefore, as long as this system is not accelerating, the normal force that the person exerts on the board happens to equal their weight. All right. So that's why I'm drawing mg here, even though this is technically the normal force that the person exerts on the whatever. Okay. And finally, I believe we had one more piece of information here. Let me do it like this. That distance was x, and let me label this way. Now, strictly speaking, I have not drawn a free body diagram here, but I just want to get through this problem. There's not a lot of angles. We saw in the solutions already. I'll do a much better job on the tricky ones. So let's just pretend this is a free body diagram, even though it's nothing close to that. There's all kinds of other stuff in here. That said, normally, what is the first step in these types of problems, according to the solution or the strategy? Do we do forces or torques first, usually?
Works.
Torque. What are the three obvious points? 1, 2, 3. Let's just do torque about A, okay? Now, before we do that, I'm going to assume this is a positive torque, and I'm going to assume this is a negative torque. I'm drawing my coordinate system in here. Do you see that? So again, what we're doing is we're envisioning A is the pivot point. Why? This isn't rotating. That means it's not rotating about A, it's not rotating about B or X or anything else. It's not rotating. That's why I can do this. So let me just say it like this. Sum of torques about A equals 0. Now, there's two forces that might cause a torque. Torque due to mg, and there's torque due to this normal force. Right? Tell me which ones are positive, negative, or are they both? According to this coordinate system, which torque is negative?
mg.
Mg. This one's positive. Again, R goes to F into the page. Mg causes a negative torque. R goes to F out of the page. NB, positive torque. Does it matter which way you call plus or minus? No. Look what you could do right here. Couldn't I just move this over to the other side? And that's what I'm going to do next. Just add that to both sides. So notice this is what they end up looking like in practice, people. You get positive torque magnitudes equals negative torque magnitudes. Again, positive torque magnitudes, all of them, maybe there's more than one in some other problem, equal the negative torque magnitudes. Whoops, that's the negatives equal the positives. All right, so far so good. Somebody help me. What should I write down for the torque due to NB? What equation should I write? Remember, we have 4 ways to do it. They were described in bullet 2D5 on page 99.
R sine theta?
Okay, RF sine theta, is that what you were saying?
Yes, that one.
Okay, so tell me what is R for this one. So to be clear, he said, can't I just use RF sine theta? And I said, absolutely. What does R mean in that equation? That was you, Jesse, right?
Yes.
So what is R for that particular force?
Would it be L?
L. It's from the pivot point to the point where the force is applied. Sweet. So it's L. What's the force? Well, that's just NB. I'll do that part. What is the angle that you see?
Is it 90 minus theta?
What's theta in this problem? See, that doesn't make any sense. Don't overthink it. Here's the R vector, right? Jesse, can you see that?
Yes.
What's this angle between the R
90.
vector? What's sine of 90?
1.
Yes. So I would say LB and just stop, because it'd be L times B times sine of 90. So far, so good?
Good.
Somebody else. What would be the torque due to mg? Remember, we've already handled all this stupid coordinate crap and plus and minus. All I need is the magnitude of it. What's that going to be? Somebody other than Jesse.
R perp F.
Okay, so he said, why don't I just use R perpendicular times F? That means I need to draw the line of action. There it is. There's the line of action for this force. What is R perpendicular in this case? I think that was Alonzo. What do you think R perpendicular is for the mg force?
Would it be X?
You got it, bro. I can't believe I just said bro. That's cool. Whatever. All right, so then the force is just mg because we're sticking in the magnitude. Voila! Oh, garçon, more wine. Okay. So in this case, we can now see, check this out. If you know this length and this scale reading, we don't even need the other scale reading. And, well, I guess we do need the other scale reading. I'll explain in a minute. And the person's total weight, you could figure out their center of mass. So this shows you how you could figure out where your center of mass is. Lay on a board that's supported by two scales. Now, generally speaking, what's the thing after we do sum of torques? We usually do the forces, right? Well, if I do forces here, the forces, I hope you agree, that's just ups equal downs. That's the sum of forces in the y direction. If you didn't know your weight, you could literally take the two scale readings and add them up and get the weight. So in practice, how does this work? You put the board on the two scales, then you zero the scales so the weight of the board doesn't show up. And then you lay down on the board. In practice, you don't just put a piece of plywood here, because I weigh 250 pounds almost. So then what you do is you put some 2x4s and put a sheet of plywood on top of it, put that on the scale, then zero it, and then your two scale readings work out. And we used to do this with kids all the time at the Friday night science shows, because for some reason laying down on a board is fun for kids. They get to see where their center of mass is. And then the other thing you could check is you can measure your height laying down versus standing up, and you gain like a 1/4 inch or something. So it's just kind of a fun bridge between physiology and physics. All right. So far, so good. Yeah, it'd be cool, right? Those are good for not happening this year, but maybe next year, right? So, all right. Questions about that? Let's get to Gonzalo's question from a minute ago. I think it was something to the effect of, what if we do this about a different pivot point? Well, let's try this. What would be, Gonzalo, you pick it. You ask the question. I did this whole problem with torques about A. And what was your question earlier? Wasn't it something about what happens if you pick a different pivot or something, right?
Yeah, because like I'm just guessing, like, because then like you'd have different like
You'd have a
forces
diff-
pointing different directions.
Yes. So let's start over. And now, do you see how cluttered even this crappy little problem got? It gets really complicated. The lines start to add up very quickly and it gets messy. So I got to erase and start over here. Pick a different point, Gonzalo. Not A.
Can we use the person's hypothetical center of mass?
Sure. So let's use this point. So now the next thing I did was what? Do you remember? Before I started doing the torques, what did I write on my paper here, so to speak? What am I drawing?
Force arrows.
Which way is positive? That's all I meant.
Oh,
sorry,
oh,
sorry. Because
like-
we want to use the. Oh, wait, sorry. You go ahead.
So like your coordinates, right? Like
Yeah, it's basically like your rotational coordinate system. You're specifying which way is positive. Gonzalo, you call it. Which way do you want to be positive here? Do you want to go this way positive or that way positive? It doesn't matter to me.
I like to go up positive.
Okay. Generally speaking, I do that too. And even when I switch over, and I'll show you. Oops. Depending on which side of the problem the pivot's on, you get a non-intuitive pivot choice compared to the mathematical definition, whatever. Next, you said use this. So let's just worry about the sum of torques about person center of mass. Okay. So what are the two forces that cause torques, Gonzalo? What do you think?
I think friction.
Nope. Which force does not cause a torque if I pick this as the pivot?
Oh, okay. So it's definitely not going to be anything that goes through the pivot then.
Right. So this is now our pivot. So what are the two forces that do cause torques?
So one is mg.
Nope. You pick this as the pivot point,
Oh,
right? Does mg act at the pivot?
yes.
Yes, because you chose it to. So that one doesn't show up anymore. What does show up? Would this force cause a torque about that?
Oh, right. It would.
How about this one?
Yeah.
Yeah, so you'd get a torque A and a torque B. And those two are the only torques. And they add up to what? In a statics problem. What is true about the sum of torques?
They're going to add up to 0.
Which one is positive and negative according to the coordinate system you chose?
So, okay, I'm going to guess A is going to be negative and B is going to be positive.
You're right. Got it? Now, give me the torque for part A. You could use any method you want. You could use R perpendicular F. You could use RF sine theta. You could use a cross product, but I don't recommend that.
I think RF sine theta would be easier.
Okay, what's the R? He said, I want to do R F sine theta. What is the R that you should use for the A force?
I could use like maybe like L over 2, somewhere around there.
No. What is the distance from the pivot to the A force?
Oh, it's going to be a minus L something.
Nope. This is just a magnitude. We've already accounted for the minus.
Okay.
What is the, now careful, what is the distance? Not displacement R vector. What is the distance? Go ahead. Was that Jacob?
Oh, no, it was me, Ishmael.
Oh, Ishmael.
X.
Sorry. Say it again, Ishmael.
X.
X. So the distance is X. So Ishmael, you're on the spot now. Sorry you spoke up, but I just want to keep things flowing. So let's try it. So Ishmael, what would I plug in then for the force?
For force would be
I want the force that causes the torque at point A. What's the force magnitude at point A? What would we call it?
It would be would it be N8?
Yes. What's the angle?
Is it 90?
Yes. Got it?
Yeah.
Okay. Gonzalo, do you agree? You good with that?
Yeah, that's what I was thinking, and I get why it's X now.
So what would torque B be, Gonzalo? This is a harder one. What's the distance you need to plug in? I'm assuming you're going to do it the same way. I'm assuming you want to do radius B, force B, and sine of theta for B. What's the radius vector we would use? Or not the vector, but what's the distance?
Okay.
And Jacob pointed out that I forgot to carry down this minus sign. So thank you. That's for the coordinates. Thanks, Jake.
I'm thinking it might be X plus something.
Okay. Well, we know this is L, and I know this is X. What do you think that is? Not add.
Maybe L minus X.
Ding, ding, ding. Winner, winner, chicken dinner. Does that make sense that this distance is L minus X? Because this is X and that's L. This must be what's left over. Add these together, you get L. All right, the force is NB. The angle is sine 90. We're off to the races. And what I was saying, Gonzalo, is this plus those two other force equations. Or I guess there was that force equation. If you recall, the force equation we had earlier was this. The two normal forces add up to the weight. I have two equations, two unknowns. I could figure out or in this case, if I didn't know the mass and I didn't know X, I could use this equation to get the mass. And then once I plug it in, I could use this. Actually, I wouldn't even need to plug it in. I could use this equation to get X separately. This is kind of cool. Notice this is a very different version of the problem. Earlier, we had to use both equations. Here, by choosing the center of mass, I could actually get the weight or the value of the center of mass separately without having to plug one equation into another. So sometimes different pivot points, you get the same final results for X and M, but there's a different process to go through. Is that good? Does that kind of fully address your question earlier, Gonzalo?
Yeah, it does. I think some pivot points are just easier.
Yeah, so to be honest, usually I like to pick either the leftmost or rightmost point in the problem. I rarely choose the middle because it gets confusing. That said, there's a time and a place for it. All right. Let me show you what else we got in here. There it is. And if you're curious about point B, I actually did it in the solution. So notice referring to Gonzalo's method, I too like to just say whatever's up is positive, but I want to point out that if you follow this all the way around, that's kind of opposite the normal math direction. So if I had chosen this point as the pivot point, it gets a little bit, so this is probably the worst way to do the problem, but it still gets it done. It's the worst because you have to use L minus X and not screw that up. And then you got to think about, oh, what's plus and minus? Oh, this is weird compared to what I'm used to, but whatever. It still works. All right. That's question 12.1. Let me stop a second. What do you think? Class, any questions on that? That's the basics. And then how does this get worse? Angles. And then sometimes instead of just using a rod, we'll use a sphere or a cylinder or something. And that I'll address probably next time. I might not get to it by the end of today. Let me show you another problem. Huh. Look at this 12.1 and a half. Now, give me just a second. Don't read it in your book. I just want to outline it here. Huh. Look at part J. Create a simulation that draws the forces as you vary the x value in time in spatial increments of Gosh, it's almost like you could code this for lab this week. That's what you're doing. So this one you're going to do in lab this week. Got it? And if you're curious, I think there's some big takeaways. And what you will find, I think, is this one is not nearly as bad as the other one because nothing's moving except for the point where the string attaches. So you put in a loop and just let the location change. It should be straightforwards. Now, that said, let's kind of scroll through this. You could see this is probably a really good problem to do before lab Thursday, right? Otherwise, you're going to be wasting time in lab. So you should do all of this in class. Look at how these pictures, I show you one picture, right? You should be able to know this problem inside and out so that the coding goes quicker in lab on Thursday. Look, here's one for the torques. Look at this separate FBD I drew for the forces. This is what I was talking about. One for the lengths and the angles, one for the torques, and one for this. And let me just scroll this down so I can get all three at once. There's three different pictures describing this. One for forces, one for torques, one for lengths and angles. It's easier to read them when you draw these separately. Done. Now, could you have skipped this problem and gone right to here? Maybe. And then you could have done torques off just these force perpendiculars, right? So there's a case where you might do R times force perpendicular. Or could you have skipped the last one and just done this one? Absolutely. You could have said, oh, well, this is just T cosine and T sine, but sometimes people screw it up when they get in a hurry and they're tired. So now, as you go on, there's a bunch of words. I'll let you read this stuff later, blah, 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 blah. You could make this plot in Excel, right? And you could see what this looks like. You could see the tension and the reaction force, but that's kind of stagnant. So what you could do is you could imagine looking at this simulation so you could see what the simulation should look like. And you could imagine drawing the arrows at different positions, right? So that's what you're going to do in lab. And hopefully that makes some sense. Questions about that? Your pre-lab is do that problem, know it inside and out, and hopefully you'll finally have a coding lab that's not going to kill you. All right? Fingers crossed. I think you can do it. I don't believe it, but I thought the last one was going to be easy too. I have a strange vision of what I think is easy, evidently. My bad. Okay. All right. So let's go back into here. I do think all this coding is good for you, so that's fine. Now let's go back to 12.2. So depending on your version, you may or not have part F. Yeah. Oh, so Alan, all I saw was like a rectangle. You know, the like little rectangles, like when you can't understand what a wingding is or whatever. That's all I saw. But
It was an emoji of two fingers crossing.
oh, sweet, man, sweet. My computer's so crappy, I don't know. All right, so yeah. Speaking of which, we'll just have a little fun here. I don't know if I've shown you guys this. You can calculate the torque required to flip open my phone. Oh yeah. Anyways, here we go. This is what we're doing. That just shows you what kind of guy I am. I'm doing all this straight crazy coding, and yet I still use a flip phone. I don't know what that says about me. Whoops, I think this is the other way. Imagine you have this scenario. Remember this one from the beginning? That's what we're going to look at in workbook problem 12.2. So, right, you can adjust this match. You can put it here, there. You can put it wherever. And if you had to guess, what's going to happen to the scale reading as you move the mass out? Will it go up, down, or stay the same? What do you
Should
think?
increase the further you go from the pivot.
Yeah, as we bring this out farther, the mass exerts more torque trying to rotate the rod this way. And look at the string. You could just watch the string stretch. Sorry if it's a little weird here, but there you go. Now you can see the scale up against my forehead. As I move this out, it's getting a little bit, whoa, this is earlier today. I dropped it. Hopefully it doesn't drop him. Yeah, there we go. I got to put this down. This is going to kill me or something. I'm in bare feet here. But yeah, so basically, as you move this out, you can see the scale reading if I do it this way. It's at about 5. This is 0 and this is 20 if you can't read the scale, which I seriously doubt you can. 0 to 20. So that's about 5. Here's the marker right here. And then when I bring it out, let me just see if I can scoot closer. Now it's up to about 10. Oh my gosh, come on. This is the last one I'll do. Here it's out to about 15, etc. So we see that this is as you expect, like Jesse was claiming. So now let's do the math on it and actually figure out the numbers. Yeah, I've definitely avoided social media. I got tired of helping out Putin, you know. So can't do that Facebook Putin machine. All right. Let's see here. Yeah. Anyways. All right. So let's go. We've got this problem. I'm going to draw it up and work it out on the whiteboard. All right. We'll find out if Putin's listening if a smart bomb hits my house any minute now. Never mess with the Putin. Don't you know, Rob? Hey, come on, man. Do your physics. All right. Okay, so 12.2. I had a question. I forget where it was. I was making fun of the, do you remember that incident a few years back? I think it was the Winter Olympics when the curling team did a bunch of steroids. The Russian curling team was found guilty of using steroids. I think it was Russian curling team. The fact that a curling team would use steroids just cracks me up. Yeah. So I love making the joke about the Putin. Okay, we got theta. We've got a large mass here. This is exactly set to the problem I was just showing you. Literally, the rod is 200 grams. The mass that I was using was 1 kilogram, which is 5 times as big. So it's literally exactly the same dimensions and everything here. We said that this has some length. I think it was L. And this was a distance X. And I think the rod mass was M, wasn't it? Let me just check. Yes. Okay, got it. All right. So this is the picture that we start with. We're supposed to draw an FBD. I could start drawing my forces right on here for this problem because it's probably simple, but it's already getting a little cluttered. Why don't we just do it over, right? Why have all that clutter? It's not that much work to redraw one rod. Give me a force acting on it. Any force.
Gravity.
Okay, mg. Where?
You can do the center of mass of the rod going down.
Okay. I hope that's in the middle. I can't see from this angle. It looks pretty close. That's
And
mg. Whoops. Let me draw that small. What else?
would you say it's also 5 mg for the block, or is that normal force?
Yeah, technically it's a normal force. However, is this thing accelerating upwards in an elevator or something? No.
No.
So then it's okay to say it should be a normal force down. However, that normal force has magnitude 5 mg. Absolutely. Okay. And then what else? Anything else?
Tension up.
Okay.
And also to the left, I guess.
Yeah. I got you. Tension along the cable, right?
Right.
Now I'm going to label that one here. What else? Or is that it?
Shouldn't there be a normal force from the rod going up against the object?
I'm going to call those reaction forces. Now, without thinking too much, I'm going to say there's one this way, and I'm going to call that reaction force X. There could also be one straight up or straight down or something. I don't know. Now, here's the deal. Generally speaking, we always just draw this one to the right and that one up. Sometimes in weird situations, this could actually be negative, or that could be negative, or both could be negative. And who really cares? It doesn't matter. But by doing it this way, if you get a negative number for your answer, you're just like, nah, it's to the left or it's downwards. So who cares if these turn out to be negative? That just means your actual vector is opposite the direction drawn. What do I recommend? Is even in problems where you know this is pointing to the left, maybe just draw it the same way every time, over and over, over and over. And if it should point to the left, you say, I should expect a negative number. That's just my take on that. Now, I could split this tension up into vectors. I could go like this. I argue that's bad form. Not because it's wrong, it's because it's usually advantageous to split this up into components that have their tails in the right spot. So this, you could actually split this up as Tx and Ty, and we know that this is theta. So you could do it that way. What is the advantage of splitting this up like this? Is there one or is there not one? I don't know. What do you think?
Would Rx and Tx be the same?
Oh, yeah, you're right. Rx and Tx have to balance because they're the left rights. So basically, Alonzo just did the forces in his head by looking at the picture. Nice. What else? Oh, go ahead.
But aren't they also both going through the pivot?
Yes. So what does that tell you?
They're going to equal 0.
For the torque problem, he's saying the lines of action of these two. So does this one. So we could see this component, this component, this component cause no torque. Beautiful. Furthermore, you could actually do length times force perpendicular and get the torque for this component. So it's kind of nice. Is it required? No. Are there lots of different correct ways to do this? Yes. But I just want to point out here, Tx is going to be equal to T sine or T cosine for this problem.
T cosine.
And that means this is T sine. Okay, great. No, Ty does not equal 5 mg.
No, not equal. Just they could potentially cause a torque.
They cause equal magnitude torques. So this tension sine theta and these combined masses have equivalent torque magnitudes, but these forces do not equal those. Think about it. This force plus this force balances these two forces, and then this torque will balance those two torques. Is that clear, Jake?
Yeah.
It's a little subtle. So what would you do next, Jake? If we had to try and solve for something, what's the next step that you might do? What would you do next?
Well, I guess pick a pivot and like do the sum of torques, depending on what we're.
What's the best
solving.
pivot to choose in this problem?
Mm,
I'll give you a hint. What are the things we know in this original picture? What are the things that were given?
So we know the length of the rod. We know the mass of the
lengths.
rod.
Mass.
see.
And
We
theta.
also know theta, I believe,
and x.
and x.
So basically, we know everything about the distances and masses. I hope you agree that's pretty common in the real world. What are the things that are pretty easy to measure? Distances and lengths. What are the things that are sometimes hard? Forces, because you usually don't see a scale in line on a building's rope, right?
Right.
Like other, yeah. So, okay. So that said, what do we not know in this picture? What do we not know?
Tension?
What's that?
We don't know tension.
We don't know T. We do know the angle, but we don't know T. What else?
Well, I guess then, I mean, we don't know the reaction forces.
So what's the logical choice of pivot?
The reaction forces, I guess.
Yeah, because
Yeah.
that gets rid of two unknowns instead of just
Mhm.
one. And we
Okay.
get one equation, boom, we're done. Right?
Okay.
So we'll get one equation, we can get the tension. Like Alonzo said, we could use that tension and the angle to figure out Rx. And if you wanted to, you could do sum of forces to get Y. Or you could do switch over to here and do the pivot point here. This still drops out. We could use that point to get the torques to get Ry. So you could actually do sum of torques about here to get that, sum of torques about here to get that, and sum of forces in the X to get this. There's a lot of different ways to go through it. Go ahead.
Cool. No, I was
You're
just saying that's cool. Thanks.
All right. So let's try writing the torque equation for this one. Actually, let's just do it this way. Let me scoot it back up. Okay. Kind of forget this stuff up here. This L is from something in the upper drawing. Tell me the torques about the pivot point. Whoever wants to go for it.
Well, we first have to do the which way is positive and which way is negative, right?
I love it, dude. Which way do you want to call positive?
Um,
Want to just go
Counterclockwise?
normal? Can we
Yeah.
just do that? I love it, dude. Okay. So typically what I do is I just work my way across. So let's just work our way across. What's the first force that's going to cause a torque?
5 mg.
5 mg. These two drop out, line of action through pivot. So Alonzo, what would you write down for the torque due to the 5 mg force?
X 5 mg
Plus or minus, according to this.
minus
Got it? Somebody else, give me the next force.
mg. So minus. Well, let's see this a little further. So
Where does mg act for the rod?
center of mass.
What's that?
So I mean, it's not L minus X, is it?
No.
No, it's L over 2.
Yep.
L over 2 mg.
What's the next torque? Somebody else.
Would it be L plus, oh, sorry, plus L T sine theta?
We got to the end of the rod, right equals 0. Beautiful. What do you think? I'm pretty sure you could do sum of forces. That's pretty easy. This plus this equals that plus that. That's the forces in the Y. And this equals that, sum of forces in the X. So let's go to the workbook and see what the heck we're trying to do here. I think we talked about this enough already. We're using it's technically a normal force, but as long as it's not accelerating, we're good. We just talked about sum of forces. Now it says, look, suppose X equals L over 4. Get a relationship between the tension and all that. Isn't that basically stick in L over 4 and you got it? We have a relationship between the tensions and the masses. We're good to go. At this point, you could solve anything you want about this problem. So let's go look at a solution and see what, whoops, I want to go to the solution. There's a couple of ways to draw it. Here's the forces in the X. Let me make this bigger. Here's forces in the X. Here's forces in the Y. Here's sum of torques about the left end. If you plug in X equals L over 4 and clean it up, you get this result. Okay. How is this practical? Why is this useful? Let's look at the next question. Let's say you have a string that is rated to support 17 newtons. The angle is known, and we have X equals L over 4. And remember, that bonus object is still 5 mg. What's the largest mass you could use and the sign won't fall down? That is a practical question. If you know how strong the string is and you know where you're going to mount a sign, how heavy can the sign be before you're in trouble of this thing falling down? Well, let's go look. So if I plug in this number and this angle, and we still assume this, just solving that for M is that. So what's the heaviest sign you could support? Approximately.
Less than 600 grams.
Nope. 3 kilograms. The object was 5M. Gotcha. You see what I'm saying, Jesse?
I see it now.
So this is one of the other things you have to watch out for. Just because we solved for M doesn't mean we got the mass we cared about. M was the mass of the rod. Now, okay, so I think that's enough on that. Basically, you solved for this mass, and then from that, it would be easy to multiply that by 5 and get about 3 kilograms. Just making sure you read carefully what was requested. And those are the issues that drive people nuts. And it's not that you don't know what you're doing, but you have to read and read carefully. Yep. Actually, Gonzalo, it's funny that you mentioned that. They usually do put bridges on wheels in this sense. I don't know if you, so in a statics class, ooh, look at this. What? Oh, yeah. Flipping it around. Let me show you something. A lot of times what they'll do is they'll take a bridge. Let's say you have a whatever. You have a canyon or a river or something. Let's say there's some water in here and you need to build a bridge. What you could do, just to simplify this bridge, let's say the bridge is a trapezoid here. If you put this bridge on here like this, and then you just try and bolt it to the ground like that, you're in trouble. Because in the summer it gets hot, in the winter it gets cold, the bridge is long enough that as it gets really hot or really cold, it can change length by enough to break the bolts. So what they do is you actually, that's called thermal expansion. What you do is instead of bolting in both ends, what you could do is you could put one end on a wheel and you let it, and the other end you could bolt to a pivot. And then as this gets hot, the wheel is free to roll and the bridge doesn't break. So there's a bridge on wheels for you. And when you take a statics class, they teach you about this. This is called a roller. Now, another thing that they'll do is they'll actually have a hammerhead looking thing called a rocker. And this is built to set in something. And they could set the bridge on this rocker, and the rocker is free to move back and forth to keep the bridge from breaking. And if you, maybe you've even seen this with oil pipelines, where you'll see these weird horseshoes built into them, right? Or maybe if you've seen this from an aerial view, they'll take roads and do, anyways, this is all covered in another section of physics called thermal expansion. But just thought I'd mention this. These principles actually apply for civil engineers. And yeah, anyways. The extremely massive weight. That's what keeps it from rolling somewhere else. Yeah, yeah, just the high inertia.
Oh, okay.
Yeah,
Cool.
yeah. I mean, when this bridge weighs a couple tons, built right, because this bridge has to support vehicles driving on it. It's not going anywhere. But that's a testament to the power of thermal expansion. Thermal expansion can cause this object that weighs several tons to move, whereas you and all these trucks pushing on it would have a great deal of effort to do it.
That's crazy.
Yeah, and if you don't account for thermal expansion, your road will be destroyed. So why do they have to put grooves? Why don't they just make one continuous thing of concrete? Because it'd be broken in a month from thermal expansion. So yeah. All right. That's why we've got to deal with joints all the time on our roadways and such. Kind of a digression, but Gonzalo, is that what you were talking about or no?
Yeah, that was one of them, but I was also
Yeah.
thinking of like there's like multiple wheels because I was thinking of like this one cartoon where like where you have to like paddle and like there's two wheels on opposite ends and it's going through water. If that makes sense.
Yeah, kind of. I don't know, but we could talk about it more in office hours too, right? So yeah, that's pretty good. I'm looking at the time. I was just getting so excited by this expansion joint, I forgot to take a break. I think this would be a good time to take a break, don't you? Let's take a break. I got 5:51. Let's basically take a 9-minute break. So come back in 9 minutes. All right. We'll pick up here. We'll do some more examples and just keep working examples as much as we can. Okay. See y'all in 9 minutes. All right. Okay, so let's take a look. Oh, I missed some stuff in the chat. Oh, okay. Got it. Okay, got it. All right. So let's go to this problem. Kind of warm ourselves back up. Now, I want you to read this question and take a guess. I've got really detailed solutions, overly detailed than what you probably need. But I want you to not look at the solutions for once, okay? So I want you to just take a second and check your own conceptual understanding of this stuff. That way, when we look at the solutions together in 2 minutes, you get more out of it. So I want you to take a second, read this question, and at on my clock it says 6:01:30. So let's just go to say 6:03:30. All right, I'm going to shut up and let you look at it. Maybe you can't rank them, but can you figure out what's the biggest, what's the smallest, and then try question B and C. So at least try to figure out which would be the biggest tension and smallest tension. I'll give you 2 minutes. And if you want, you could private message the other people in your lab groups if you want to converse about it or talk or whatever. Okay, so you've had a second to think about it. It's okay to not know what's going on. But again, physics education research indicates if you respond and take a guess, you'll get more out of it when we do go through the answers. So, does anybody want to take a guess which string they think has the largest tension? It's okay to
D.
be wrong. Oh, go ahead. Say it again.
D.
B. Why do
Or
you
D.
think? Oh, D.
Yeah.
Did you say B or D?
D.
D. Okay.
Yeah.
And what is your reasoning behind that? Or
Um,
what are you thinking about, I guess?
so the well, first A and B, it's the tension is at an angle.
Okay.
So that means that it's split into components. So one goes to the tension Y and one to the X, but the X is supported by the pivot, I think.
Okay.
So those are,
Balanced by the pivot. I would say balanced by the pivot, but yeah. Okay.
yeah, while C and D aren't split into components, it has to hold all the weight. Well, the string has to hold all the weight.
Okay. You're
And
on the right track, but it turns out you said it exactly backwards.
oh,
Now, let me rephrase. If I said it like this, do you agree that TX can't help support the block? Do you agree with that statement?
yeah.
TX and the pivot are pushing left, right. So TX does nothing. Do you agree that TY still has to balance the block vertically? And so the idea here is when you compare these, which force is going to be larger, a Ty without a Tx or a Ty with a Tx? Which force would be larger? A tension with a Tx is larger than a tension without. Alonzo, do you buy into that? You'd have to do square root of Tx squared plus Ty squared. You know what I'm saying? And that makes it bigger than Ty by itself. Alonzo, is that better?
Yeah, I can kind of like picture it right now.
Yeah. So it turns out that was not correct. D is not correct. In fact, now that you know that, where do you think D ranks?
The lowest.
The lowest. So this is the minimum tension. Whoops, I think that's supposed to be a Ty there. Sorry if it's sloppy. All right. So actually, we expect this one to be the least tension because the string is perpendicular. If the string is perpendicular, all of the tension goes into producing torque. Whereas when the string is at an angle like this, only some of the force goes into causing torque. Is that why it's harder to hold our arms at an angle versus all the way up? Yes. That sums it up, Gonzalo. You said it. Because you have to balance the torques with your shoulders, not just the forces, right? So going to this, why is it easier to do? Well, now here you also have to lift the arm, but so there's a couple of different things about physiology that I can't go into, Gonzalo. But right, if you put if you hold your arm out here versus like this, for example, if you were doing shoulder raises and you bend your arms, it's a lot easier than doing shoulder raises with your arms straight out, right? So you always see people in the gym trying to cheat and like lift these huge weights, but then they bend. It's like, what's the point? Just use 10 pounds all the way out. You're going to get a huge workout. Right, Mark? You there? You know what I'm talking about? Mark, I think Mark does some lifting, right? He mentioned that earlier. So he's probably
Yeah,
seen
dude.
it.
Oh, my bad. I was on the wrong mic for a second.
Oh, no. Yeah. All right, cool. So yeah, small weights at a large radius, you get a massive torque and it's a huge workout. So yeah, I used to work out with this guy, Kenny, and Kenny was a much smaller guy than me. And so in particular, my torso is very long. So yeah, I've got a very long torso. And what would happen is when we would do press or something like some kind of chest press or whatever, I would destroy Kenny. But then because he was so much smaller, when we were doing fly exercises where you're having to rotate, he'd have a much smaller lever arm and he would destroy me. So in that sense, we were good workout partners because we both kept pushing each other in different types of exercises. It was fun. Hey, Kenny, if you're out there, word up, man. Kenny Rosenberg. All right. Let's see. Anyways, I don't even know where Kenny is these days. Yep. Bench versus fly. Yeah, or bench versus press, excuse me. Yeah, whatever. Yeah, fly versus press, I guess is what we should say, right? All right. So in this case, all right. Sorry, let's get back to this one. My bad. I digressed. All right. Which one of these? So we think this is the least tension. Which one do you think has the most tension now that we've discussed it? B, right? The string's at an angle, and when you have the string way out here, the tension is basically half of the weight. Think about it. If this is mg and the lever arm is L over 2, well, here, if I use twice the lever arm, the tension only needs half the force. Agreed? If I use twice the lever arm, I need half the force if both things are applied in that perpendicular fashion. Now, how does this situation compare? I use half the lever arm what must be true about the tension? If I use half the lever arm, how does the tension relate to mg?
Is it gonna equal mg?
Nope. Remember, I could write the torque equation for this. Tension times L over 2. That torque magnitude should equal L times mg. Run it again, Gonzalo. What do you get? How does tension relate to mg?
Oh, it's greater. Double.
Yeah, that is not a smart design for holding this, but sometimes you don't get a choice in where you have pivot points and where you can attach different fixtures to your ceiling. So maybe you have to do this. Whatever. So now, what is that going to mean for this one? Oh my gosh, it's going to be through the roof, right? Because I need the vertical component to be 2 mg, and then the horizontal component is going to be something else. So you're going to get a massive tension, much bigger than. So the only question is which one of these two is bigger, and we could discuss that later, but whatever. All right. So how about in which situations? Sorry, let's do part B. In which situations, if ever, will you have a reaction force at the pivot pointing left? Under what circumstances can you have a component pointing left at the pivot? A, B, C, or D, or none of them?
Would it be A?
Let's think about it. The string is pulling this way, right? There's the tension. Is that string going to push the pivot into the wall, or is it going to pull it away from the wall?
I think into.
Yeah, so here it's going to have the wall, like the pivot's got to push the rod outwards because you have to balance this TX. So does that make sense, Alonzo?
Yeah.
If the string jams the rod into the wall, the pivot pushes the rod away from the wall. Based off that, now which one do you see it? B. Right? This one's got a component away, so this one's going to have to pull it to the left to keep it from pulling out of the wall. Okay. So this is obviously a little bit nicer for your fasteners. You don't have to worry about it flying out of the wall because the rope itself is helping it stay in the wall and the screws don't pull out of the wall. These two over here have no horizontal components, agreed? So there's no force Rx for those two. Finally, what about vertical components at the pivot? Are there going to be any situations where the pivot actually pulls down or not? Or is that just nonsense? What do you think?
They all have tensions going up, right? So it's going to have
The
to pull down
tension
in
is
all of them.
always pulling up. Well, wait a minute. Remind me. Let's start with D. D is kind of our classic, right? We know that this is mg. And I know that because the tension is twice as far away and perpendicular, I know this is mg over 2. Jacob, is that tension enough to hold up the rod or hold up the system?
No.
So what force do I need at this pivot?
Oh, so you're going to have mg over 2 again, right?
Yes, got it.
Okay.
Does that make some
Okay.
sense?
Yeah, I see.
So let's think about this again now that we've kind of done our base case. In this case, we know that there needs to be a force up at the pivot to help balance whatever the string didn't hold up, basically. So which case looks most similar to D, if you had to guess, in your opinion? I could see lots of different answers here. Just go with it.
A.
A, because it's pretty darn similar to this, but you just add in an X component, right? So basically you add in these two arrows, it's otherwise exactly the same. All right. So what about, so do you agree this one has to be up? Adding in an X
Yes.
component doesn't help at all with the upwards. So how about B or C? Do you think it's basically the same thing or not?
So C, the tension is double. So I think it does. It's going to have to point down there at the pivot, right? Otherwise, it's going to start going up.
Exactly. And do you agree that this one would be exactly the same as that? So in the set, but with X components.
Right.
All right. So you got it. Let's go look at these solutions now. You can learn a lot from this problem, I think. So I did all the torque equations and look down here at the bottom. There's the FBDs for this now. And I drew them somewhat to scale, approximately to scale. Now look at these. Which of these looks like the stupidest possible way to bolt something on? Which one is just looking stupid? Or let me rephrase. Yeah, it's a terrible design. Now, there may be a reason you have to do this. So I'm not saying it's not one to consider, but this would be your choice of last resort because you're supporting the same block, but the other forces are huge. This is not a good design. Whereas here, look at this one. You support this block. This is why usually tables have legs at the corners. Shocking. But, you know, you maybe have seen a table that has a support in the middle. And this is a bad idea from a torque standpoint, because if somebody pushes right here, the table tips over. So then you have to have a huge mass in the middle, and then the table is hard to move, but you can get your feet under it. So it's not that there aren't reasons to have these weirdo designs. It's that you have to think carefully about safety if you do it that way. For example, this design right here, it's very obvious. This is, what if you don't have a ceiling? Well, then this is the way to go, right? Yeah. I'm fresh out of marble tables personally, but yeah. Marble table, right? A big dense table wouldn't flip very easily. Ah, I gotcha. Yeah. So this is what you have to do if you're going to design objects that people use, is you need to think through these different scenarios and say, what's the least likely way someone's going to get injured? How can I design this? And that's what this chapter is all about. So, and to be honest, you could design equipment in a lab if you're not doing this, you know, but whatever. So there's times you might, there's times you might use this kind of reasoning, even if you're not doing physics. Here's another one. Why should you bend at the knees when you're picking up heavy objects? Now, normally I bring in this demonstration to the classroom, but this one is extremely heavy and difficult to move. So I'm just going to skip to the result here. If you think about it, this tension's at a really big angle, right? From 90 degrees. So there's very low torque for the amount of tension you get. And so if you bend over, right, this, you could imagine this would be like your legs. It's a really crude model. And this is your back or your spine. And these are the muscles called the Erector Spinae. This is a very simplified model of the Erector Spinae. Okay, but they actually are a bunch of different, it looks really like this, where they connect at different spots and there's different angles. So I'm just taking the average value of these. But so all of these different muscle fibers connect to the different spine segments. And on average, you could say they kind of look like this, but 12 degrees, right? Sine of 12 is a very small number. That means if you want to have enough torque to keep this crazy ass object from tipping over, you need a massive tension in your back muscles, and you throw out your back. So if I could go to that one, do I draw the picture? No, I didn't, but that's the basics of that. So if you're wondering why you bend at the knees, you could change the orientation of your spine, and that brings the masses closer to your center of mass, right? And if this mass, right, if you try to lift this thing like this, let me just go to the whiteboard. Right? Imagine if you tried to lift this thing. Sorry, give me a second. If you redid the model of your body like this, where you bend less here, and then you have 2 pivot points here, and then your arm is hanging down. Notice this mass that's hanging down. This would be where the dumbbell is. Let's put a head on this guy here, or girl, whatever. Right? Notice this mass is a lot closer to the pivot point. You get a lot less torque. You have a lot less trips to the hospital or to the Valium factory, okay? Or whatever that is. Muscle relaxant. I don't know, whatever. Do not trust me with your medical advice, right? I don't know where you go for so I just try not to get injured. I'm just perfect at everything. And these, why would I ever get injured? That would never happen to me. Whoa. Okay. I don't know what I'm talking about. So, in short, bend at the knees when picking up heavy objects. If you're interested in this, you could read more about this, and it's pretty complicated and blah, blah, blah. Let's not go into it anymore. Should have dropped more acid. Gotcha. All right, next. We're going to do this ladder problem. All right, so somebody just tell me a force that's acting on the ladder right now, and take a second to read it first. I don't want to rush you. Got a ladder, leans up against the wall. We're going to assume there's negligible friction between the wall and the ladder, but there's a coefficient of friction between the ladder and the floor. What do we get here? Let me just draw it up here. That was approximately my torso to scale. That's disturbing. All right. Ladder. Obviously, there's a wall here, a floor here. I think we were told this is theta. What's one force that acts on this thing?
The force of friction to the right.
Okay. Friction, right? This ladder is going to try and slip out. So the friction's going to point that way. I agree. There's got to be some friction. Okay. I'm going to call this friction 1, even though there's no friction up here. What else? Go ahead.
The center of mass of the ladder, mg down.
Okay. Somebody else. What do we got? What's another force?
Normal force at the top.
Which way is the normal force at the top?
To the left.
Yep. And then, Denna, if there was friction at the top, which way would it point if you had to guess?
Upwards.
Yeah, right. Keep this thing from sliding down. So what we'll do is we'll say friction 2 should point upwards, but it's approximately equal to 0 in this particular case. One of the homework questions I ask you about says, say this is non-negligible. Then how do you do it? So that's why I'm alluding to that. Anything else?
Reaction forces at the bottom?
No. There's no actual pivot in this problem. However, what is the other force at the bottom?
Normal.
Normal.
Yeah,
Normal. Now, in this case, the normal force at the bottom and the frictional force at the bottom are effectively the reaction forces. If you imagine this was a pivot, aren't these effectively Rx and Ry? And so now we see how you do problems if there's no pivot drawn. You just draw the forces, and some of them are effectively the reaction forces at the pivot. All right?
Wouldn't they be translating to the left?
I am assuming this ladder is not slipping. So it's not going to slide out. Is that good?
Yeah.
Yeah. All right. In fact, what would it look like? Well, I was so proud of this. I needed a ladder for class and I was running out of time. I'm like, oh, I just drilled a bunch of holes and stuck some dowels. It's like, oh yeah, I just think this is so fun. Anyways, I was so excited that this worked 15 minutes before class. So what I'm going to do is I'll show you. It's not slipping. Not slipping at all. Got it? Right there's the ladder kind of running down there. It's the ladder to the Carrizo plane. There we go. All right. So let's get back into there. Oh, wait, what were we doing? Oh, we were drawing forces. That's what we were doing. There it is. All right. So do you agree? Somebody tell me the force equations, not Alonzo, because he did forces on the last problem. So somebody other than Alonzo, tell me about the forces in the X direction here. What do you get from the forces in the X?
Friction 1.
What about friction 1? That's one of them.
That will be use of S.
No, let's just call it friction 1 for right now. Just hold on. What are the other forces in the X direction? Because I want the sum of
the second normal force.
Yeah, nice. Would it be plus or minus?
It would be minus.
Yeah, nice. And that would be it. So I'm just going to cheat and move it over. Are you okay with that? Was that Alan?
Yeah.
Yeah. Are you okay just switching it over like that?
Yeah, that's fine.
Sweet. Somebody else. How about forces in the Y?
N1 plus F2, but that's 0. I guess we can write it though, and then minus mg. Right? Something like that. And then what's the torque equation? Well, before we do torques, you have to pick a pivot. What's the best choice of pivot for this problem? Down at the bottom, why? Because we eliminate 2 forces and then we only have to do 2 torques instead of 3. Let's do it. Okay, start at the bottom. Work your way over. What's the first force that causes a torque? Not these, because at the pivot or line of action through pivot, mg, does that cause a torque?
Yes.
So how do you want to do that one?
You still do RF sine. Nope.
Okay, let's do it. So let's say, do you want to call this way positive?
Yeah, because then it's falling, right? Or it wants to fall.
Yeah, it doesn't matter either way. So I'm fine with that. I like your reasoning. Sure. We might think it tends to rotate that way, so why not call it positive? That's what he's saying. I'm totally cool with that. So, Jesse, why did you go ooh and change your mind? Walk me through what you were thinking.
Because of the angle.
Oh. Okay, what is this angle right in here?
That's 90 minus theta.
So you caught yourself. So it's not sine of theta. It's going to be
sine of 90 minus theta,
which equals
cosine of theta.
Money, 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 money. All right. What's that distance, Jess?
L over 2.
Yeah. So what's the torque due to mg? You said it.
L over 2 cosine theta?
Nope.
Wait, L over 2 mg cosine
theta. RF sine of 90 minus theta, which happens to equal cosine of theta. Worst song ever.
Oh, and positive because, at the direction.
Yeah, and it's positive because we said we chose to make this positive. Does it matter? No.
What's the other torque? I'm going to run out of room here. So I'm going to say equals, and then what it equals, I'll put below here. Somebody other than Jesse or Alonzo, they both contributed here. What do you think is, and Alan also did. So somebody other than those three, what's the other force causing a torque?
N2?
N2. Yes. So what does the torque do to N2?
So we have R is going to be L, I believe, and then the
Okay,
angle.
R is going to be L.
So I'm going to
Force
do
is
RF
going to be
sin
N. Can I
theta.
say the force? R,
Yep.
F, and then what's the angle we need?
Now theta is 0?
It's theta.
Oh, okay.
So notice the geometry we got to do, that alternate whatever parallel line stuff. That's a very technical way of, that alternate parallel line stuff. I'm tired. Who cares? I don't care about the names of these rules from geometry. All I care about is geometry, right? So in this case, that's the sum of torques. 3 equations, 3 things we don't know. N1, F1, N2. What are the things you typically measure in the real world? The length of the ladder and its weight. You could get the angle of it by looking at it and doing some XYZ, tan, trig, whatever you want to do it. Okay. That's the core of the problem. After that, it's just solve for something. Now, I forget who spoke up earlier, and I apologize for not mentioning you by name. Who was it that was talking about F and the mu static? Go ahead and speak up again.
That was me.
Okay. Was that Alan?
Yeah.
Okay. So Alan, in this case, I just want to point out that friction 1 is not mu static. I think you meant mu static times normal force 1, right? Remember that friction is not mu. Friction is mu times a normal force. However, in this problem, is that thing about to slide? If it is about to slide, if I bang on it, it should fall down. It's close, but not quite. It's not quite. So we see in this case, it's not on the verge of slipping. It's close, but maybe not quite. So this is not true. In this case, it's not on the verge of slipping. Is that good, Alan?
Yeah. Thank you. I was just
go ahead.
basing it off of the book because it says the coefficient of the static friction between the ladder and the floor is nu of S.
That's right. And so that was decoy information that's not useful.
Oh,
It was a
okay.
trick. However, part D, I think. Let's look at part D. There is one of the parts where you assume it's on the verge of slipping. Look at part D. What is the minimum coefficient required to keep it from sliding? That's the key word that says, aha, that's when I can use mu static. Does that make sense, Alan?
Yeah.
Part D, we basically say, yeah, mu static times the normal force. So let's go in and look at it. So at onset of slipping, that's when we use that result. And notice I get this weird cotangent crap. All right. So far, so good? All right. So now what I'm going to do is I'm going to do a variation on this. Let me just show you, and then I'll come back. Sorry, the headphones don't reach. I'm getting this to where it is on the verge of slipping. Right about here. On the verge, right about there, right? All right, it's a little bit tricky. Give me a second. It's a little bit different every time at every different spot on the table. Okay. It's very, very close to slipping. And notice each time I move it to a different spot, the angle changes because the frictional coefficient changes slightly depending on which spot on the wood you're sitting on. So now you see this little mass that I have right there? I'm going to take that mass. It's mg L/2 cosine theta, I think, or sine theta, L/2 sine, something like that. But yeah, I'm going to take this mass and I'm going to stick it on this second rung of the ladder. It's on the verge of slipping or very close to it right now. When I take this heavy mass and I put it on there, what should happen?
It slip.
Okay, let's see. I better be careful. I'm going to break my furniture. Oh, shit, I did. I got kids. I'll blame it on them, right? Teaching at home. Time to get some reimbursement from the college, right? Oh, shit, I really messed that up. Okay, do you agree it's not slipping? You put that extra mass on there, it's less likely. What is going on? The next problem in the workbook. Let's take a look at it. If you run this thing again, if you put an extra mass on here, you could this is basically that same problem where we had the rod this way, and then you put a mass here versus a string here versus in a different spot where you put the string here and a mass here. Man, I can't believe I broke my furniture. That's dumb. But in this case, if this mass is close to the bottom, what happens is more of the weight shifts to this, right? And this force gets bigger. And as a result, you have more possible friction force. Now, let's see what happens if I put it on up high. It easily goes. So this is a serious problem. The ladder, when you first step on it, feels really good, feels really stable. But when you walk past the center of mass, the physics equations flip, and now you're making it more likely to slip. So you step on the ladder, feels really good. Let's go. Climb up, fall down, break hand or face, not good. So that's somewhat interesting. All right, questions on that? Whew. All right. I find that interesting anyway. So you could do this one, ladder part 2. It's very similar. You just added an extra term and then blah, 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 blah. Okay, you could do the math with different values of X. Boy, this was just begging out for running a simulation, right? You could run this at different positions and literally see when it should slip and when it shouldn't. And you could do the calculations on the frictional force if you knew a coefficient, and would it exceed the maximum possible or not? At some point, you run a simulation. If you discover that the F1 required to keep it still is larger than mu static times N1, then you know there's not enough possible friction to stop it from sliding. Enough said. All right. All right. So that's the zombie ladder. I want to talk about this one, 12.7, and we'll call it good. Then next time we're going to pick up on these ones that have cylinders on it. All right. Or spheres or something. So 12.7. In this case, I'm going to write this down. You take a second to look at it. .7. All right. Oh, and okay. Before we get ahead of ourselves, I don't know if you remember what was one of the things I suggested at the beginning in terms of drawing pictures. What's one thing we might want to do? You're tired. Screw it. I'll tell you. Draw a picture with just lengths and angles. And you might have been thinking that, but that's what I was going for. So before we draw the forces, let's first make sure we understand the lengths and the angles, etc. There's a picture here. There's a block right here. This distance was X. Now, in this case, I actually want to leave this one off for a minute just because it's going to add some confusion. What is known? Let's list the knowns. L, so these are my givens. Length was given, theta was given, X was given, and I think the mass was given. G is a given. But I don't think we knew alpha or beta in this problem. Let's look again and make sure. Oh, we also know this distance y is 2/3 L. Okay. So I know this distance right here is 2/3 L. How do I figure out alpha and beta? Now, I know you can read the solutions, but let's try and work through it, all right? Help me. What would you do in this case? And this is kind of tricky if you haven't done it before, but once you do it, it'll become automatic. So it's okay if you're stumped.
Well, A says use geometry, so I guess geometry.
Yeah, what would you do to, like, so I know L and theta in this length. How do I get alpha or beta?
Well, we know theta is 85 degrees, so
Okay.
opposite of theta is going to be 105 degrees.
You mean 95, I think.
Yeah, sorry, yeah, 95.
So you just did 180 minus theta right there, right? Okay, that's a good start. Now what?
I think we can also get angle alpha by, I forgot what this rule is called, but it's like interior correspondent angles or whatever. I forgot what it's
Okay.
called.
Okay. In what way then? What do you like? Do you know an equation that comes out of that formula or not?
I think it would be 85 because if we have another line that goes through.
No, that's this case. If you had this one, and then like let's say we go this way and then this way. If these two are parallel, then this angle here, whoops, sorry. If this was 85, then this would be 85, but we don't have that, right? We don't have this line coming over that way. Whoops, jeez. We don't have this. So that's a good thought, Alan, but I don't think that particular one is going to work out for this. And maybe I'm just misunderstanding you, so I'm sorry about that.
Oh yeah, that's what I was thinking.
Yeah, but that doesn't work out. Go ahead, Alonzo. What do you think?
The sum of torques?
No. Okay, in the interest of time, I'm going to show you the trick. We are good at right triangles, not oblique. Make this a right triangle. Boom. What is this side? Well, this is L cos theta. What is this side? This is L sine theta. Now, tangent of alpha should equal this over both of those put together, meaning L sine theta over the sum of these two. And now that you do that, what drops out?
L.
You got numbers, you plug them in, you got alpha. Once you get alpha, what's true about this angle, and that angle?
They sum to 180.
Furthermore, just for kicks, what's this angle right here with the question mark?
90 minus beta.
No.
Beta?
This is a vertical line. 90 minus beta would be that. It's not 90 minus. You see, I'm warning you. Yeah, these problems get sneaky. What is it, Alonzo? What did you think?
Theta?
Say again. I couldn't hear you.
Just theta by itself?
Nope, it's not theta. It's alpha. Mark got it, I think. This is what Alan was saying earlier. This, that, whatever rule.
Oh yeah, that's what I meant.
the this, that, whatever rule. It's a very common rule.
Yeah.
All right.
I never thought I'd see geometry again.
It's just simply the corresponding angle.
Yeah. Yeah. And I think that's what Alan called it, the corresponding. Yeah. Okay. So to be honest, these are all the tricks that we have. So what is the last trick I wanted you to see in here? You don't need to retake geometry. You just need to do all the problems in this chapter and you'll be good enough. Trust me. So, yeah. But when we do this one, I know we're over. I don't want to take too much time, but I do want to show you just the solution to see where you would go from here. That way you could do this one at home. Okay. There it is. And so from there, forces, torques. And usually we do torques first. Now, oh yeah, Karen Tate, that was awesome. Yeah, she's retired now. COVID finished her off. She said, I can't take teaching anymore. So she retired. I'm so jealous. Hopefully she's doing well. I haven't talked to her in a long time. This is what I wanted to point out. Okay. Look at this T cosine alpha. Do you guys see where T cosine alpha comes from? Whoops. Oh, that's T sine alpha. I flipped it. Do you see where the T sine alpha comes from? This is alpha. The horizontal component in normal XY coordinates is T sine alpha. It is not related to beta. Beta we use for the torque equation because beta is the angle between the tension and the R vector that goes this way. Oh, don't you love it? So what we see here is the way you split up the tension vector for the force equations is different than the way you split up the tension for the torque equation. And this is why this chapter is tough for people. It's because there's a lot of little details to screw up, even though you know kind of what to do. And the devil is in the details, so to say. We better stop. Was there one last thing to say about this? I don't know if there was. If so, I'm so tired. I don't know anymore. Okay. Yeah, and I do want to say one last thing. That was it. I want to notice 12.10, file under potentially painful grinder. What do I mean by that? This problem can be hell if you don't see what to do. So just to allude to that, 12.10, I just want to show you. I drew lots of different pictures. Here's the way that I first thought to do it. Then I said, wait a minute, couldn't I split this into components? That works. And then wait a minute, once I draw the components, couldn't I redo this thing with lever arms? And couldn't I do this with levered arms on the components? So 12.10 is a really, 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 really good problem to make sure you got this stuff automatic. It's got all the tricks, use the solutions, do it. That's the end of the live stream.
Well,
go ahead.
Wait a minute. Isn't it also kind of like the drawbridge earlier? Like just
it's just like this one. So you could do it. Yeah, you could do this one with lever arms and such. Every different problem gives you different pieces of information. So you could argue you could do this one, and I kind of foreshadowed this in the solution we just looked at. You could do this with lever arms if you want. You could do it with lever arms on components if you want. Or you could do it with RF sine theta if you want. Or you could write them all as vectors and do R. You could do it with force perpendicular if you want. There's lots of different correct ways to do it. Only when you practice it and do it yourself do you really get it. That's it. Is that okay, Gonzalo?